Mass transfer. So, what is the mass transfer? Mass transfer represents the last contribute that can create overtension, looking about the cinetic of an electrochemical reaction, an electrochemical process. So basically, recalling for a moment the different types of steps that we can appreciate during the development of, for instance, one reduction, or maybe even the opposite reaction and eventually oxidation, we know that basically the reagent need to pass through different steps of obstacles. For instance, we can have eventually some chemical reaction, we can have an absorption, we can have the real core of the process, the electron transfer, and then we can even have at the very beginning a mass transport, the diffusion of our reagent from the bulk of the solutions until to reach the surface of the solutions, the interface between the bulk and the electrode. So basically, we know that each of these single steps, each of these single obstacles is associated with a specific resistance that fight our process in order to obtain something that is close to the ideal condition. So basically, what does it mean? That for each single resistance, we have a connected overtension. So each of these single steps can cause a loss of energy, basically, when our reactions is proceeding. And so until now, we have described, for instance, how speaking about the Butler-Volmer equation, the electron transfer is able to affect with certain over potential the loss of energy. And we have described, for instance, considering this one, the electron transfer, as the limiting step, what is actually the function over potential versus the current. So how much strong is the energies lost, quantified in terms of over potentials in accordance with the current. That is a function of how faster we are proceeding with our reaction. But now what is important to say is that the electron transfer or also the ohmic resistance are not the only one types of obstacles that we can observe during the development of an electrochemical process. So another extremely important resistance, and so another important contributor due to the generations of overtensions, is still remaining in the mass transfer. And so the mass transfer represents the phenomenon inducing loss in energy associated with the migrations, diffusions, or in general the movement of one species from the bulk to the surface, for instance here and here. Now what we want to do is try to solve the same function over potentials versus the current, but in this case taking consider about what? Taking consider about the mass transfer. And so in which way, for instance, the diffusion and the concentrations, maybe gradient, between the bulk and the surface is able to induce the generation of overtension. So, before start the description of this function, it's important to say that the mass transfer obviously is considered in order to solve this as for what concerns the same situation that we have used in the Butler-Volmer equation derivation, we are considering the mass transfer as the limiting step. So now we have described how basically in the Butler-Volmer plot we have this particular trend imaging that the electron transfer is the limiting step. Now we are doing the same for the mass transfer, and only later we can mix the two contribute and obtain the final well-known described in the first lesson speaking about kinetics concerning what is the real profile of overtensions versus potential when we are merely polarizing to an electrode. So in this case we are considering the mass transfer as a limiting step. and so the slowest. This step that describes the overall kinetic is just an assumption, but in general we can say that this step, these assumptions, is quite reasonable, especially when we are working at very high current. And in particular, it's true when we are approaching the limiting current. What does it mean? If we remind the general plot concerning the variation and the generations of overtension versus the current density, we know very well that the real behavior it will be something like this. And we know that this behavior is associated with a contribute due to the electron transfer, this one, electron transfer, a contribute due to the ohmic resistance, so ohmic resistance, and we have a contribute due to the mass transfer. So we know that, and we have described this, when we are looking for a situation inducing a low current, so when the process speed is quite low, and so also the overpotentials are low, the relationship is quite well described with the Butler-Volmer function, so in according with the electron transfer. So the electron transfer represents the obstacle that is more important when we are working at low current. Increasing this current, basically the most important contribute is the one due to the ohmic resistance, since we know that the reaction not visible due to the dynamic equilibrium that is broken is not so important as in the case in which we are working at low current. All these concepts are quite well described, speaking about the Butler-Volmer in one of the last lessons. So, but when we are approaching very high current, we can appreciate how the total trend is quite similar with respect to the one of the mass transfer. Because imagine that it will be the limiting step. By solving this equation, this function, we will see that the trend will be something like this. And we can appreciate how the total one is basically extremely close with respect to this one when we are approaching very high current, and in particular when we are approaching the limiting current. What does it mean? That if we increase more and more the polarization, maybe if we are polarizing one electrode negatively, what is happening is that polarizing these more and more, we are forcing our reactions to increase the speed. But there is a point in which even if we are polarizing more the electrode, so we are increasing the potential, we are increasing maybe the overtension in an electrolytic cell, what is happening is that we are not able anymore to increase the speed. So exists a physical limit over which we are not allowed to go. So we are not able to surpass and overcome this limit. Even if we are polarizing the electrode a lot and a lot of the lot, at a certain point we can reach a situation, and this situation represents the maximum achievable speed, the maximum current. And so even if the potential increases, the current is still remaining the same. And this current value takes the names of limiting current. And the limiting current, and so the maximum speed we can achieve, even if we are polarizing more the electrode. Obviously I'm speaking about an electrolytic cell, so we are imagining to applying a potential in order to favor a process, in order to speed up the reaction. But these reactions cannot be speed up over a certain value. And this is due to the fact that a limiting current exists, and this limiting current exists because we need to take in consider about the concentration, the concentrations of our species in the bulk, the species that need to undergo eventually oxidations or reduction reaction. When we have no more sufficient amount of species Because we have a certain fixed concentration. This fixed concentration is associated with a limiting current. And we will see in which way increasing the bulk concentrations of our species lead to increase also the limiting current. So, but before this, it's important to say that in order to solve this function, imagine that the mass transfer represents the only one step, the limiting one, assumptions reasonable for a very high current situation. It's important to remember that the mass transfer is associated with the definitions of flux. So if we are speaking about the flux for one hypothetic E chemicals, we can describe this in this way. And the flux is basically having unit of measure mole per second centimeter square. It's basically the sum of three parameters. And these three contribute are respectively the diffusion plus the migration plus the convection. So the diffusion, basically, it represents a movement of chemicals under a concentration gradient. We will see later this better. So we have the diffusion coefficient and the concentration gradient versus the space. Then we have the migration that represents a movement of species under a potential gradient. So here we have RT, the concentrations in bulk, the diffusion coefficient, and the potential gradient, so filling the presence of different charge on the surface of the electrode. And then we have the convection, so that is basically a contribute that is equal to the concentrations of the bulk for the intrinsic speed of the fluid. So now basically we have these three contribute, the diffusion, the migration, and the convection. Now, for simplicity, is important to consider the fact that in mass transfer process, for the resolutions of these functions, often we are only taking consider the most important contribute, that is the diffusion. So now, what we are doing is assume to make these two parameters negligible and focusing our attentions on this one. So this particular type of relationship, if you are eliminating these two contributes, is basically a very well-known law, and is the Fick's law. It is the law that defines actually what is occurring during a diffusion. So we have a flux of species that is in contrast with the concentration gradient. And this is the reason for which here we have a minus signs. Why? Because the flux is directed toward the direction in which the concentration is smaller. Why? Because the diffusion is a statistic process. What does it mean that diffusion is a statistic process? And in which way the Fick's law describes this statistic process? So if we want to represent graphically what actually is the diffusion, this is the first Fick's law. We have even the second one, but in this case it's not so interesting. We have, for instance, our electrode. This is the electrode surface. And we have our solution. Maybe we have here a certain amount of molecules, certain amount of species, that are the species involved in the electrochemicals process, and maybe here the amount of species when we are far away from the electrode is higher. This is a classical situation. So the concentrations in bulk, when we have a real process, so we are rerunning actually current, is the concentration in the bulk is higher than the concentration of the surface. Why? Because this on the surface, this A chemical is converted maybe in another one, in B. And so if we are focusing our attentions on A, it's quite obvious that maybe what is happening is that proceeding towards this direction, we have on the surface a conversion. And so when we are getting close to the electrode surface, since these chemicals are going to be transformed in something else, the concentration here is probably smaller with respect to the concentrations in the bulk. Because one molecule arrives here and is converted in another one due to an electrochemical process, a reduction or an oxidation, and so on. When we are away from the electrode, obviously we can have an higher concentrations because any types of transformations and any types of reactions are occurring. So basically here what is happening is that we have a gradient in concentration, an higher concentration here and a smaller concentration here. And so the diffusion, the Fick's law tells us that since this is a statistic process and since chemicals can migrate in each single direction, the probability of migration from this side to this side is higher with respect to the probability of migrations from this side to this side. Why? Because here we have more species, here we have more molecules, and so the probability of migration in a zone in which we have more molecules is higher with respect to this probability. And so the system spontaneously tries to homogenize itself. So knowing this, basically, I have also introduce the fact that the concentrations profile of our chemicals toward the surface of the electrode is decreasing. So if this represents, this is the distance from the electrode, for instance, so this is 0, it means that we are looking for a situation in which we are basically attaching the electrode surface. And here we have the concentration. We can appreciate how basically the trend of the concentration starts from a maximum and then decrease in this way or in this way, and so we have an asymptotic trend. These represent the bulk concentration, the maximum one, where from a theoretical point of view is achievable only when we are approaching a distance that is going to infinite. So the limit of the concentrations for a distance that is going to infinite is the bulk. Whereas when we are close to the electrode, we can have the minimum concentration. So when the distance is approaching 0, the concentration is minimum. It could be 0 or it could be an other value, maybe not 0, but it's also minimum. So now what we can do is consider the fact that in this situation, the speed of migration is proportional to this gradient variation. So the speed of mass transfer is basically a function of what? Of the difference between the bulk and the surface. So basically an infinitesimal variation of concentration versus the distance. What does it mean? Why I'm saying that the mass transfer speed, this is let me write it better, that is not clearly visible. So the mass transfer speed, this is the mass transfer rate, if we want to be more precise, is a function of the variation in concentrations for a variation in space. It's obvious that this is correct, because basically if we have an higher variation in the concentration versus the distance, it means that the mass transfer is proceeding faster. Because if this difference is higher with respect to this one, the mass transfer is proceeding faster. So it's basically a sort of speed. The speed often is the variations of space versus time. In this case, is a mass transfer speed, so it's a variations of concentration versus space. Higher is this variation, higher is the speed. So, but this is basically more precising, is also equal, since we are imagining that the only contribute is the diffusion, equal to d for this. This is the diffusion coefficient. But it's quite difficult to imagine to solve something like this. This is a differential equation. And so what we can say is proceed with an assumption that is known as Nernst linearization. What is the Nernst linearization? Well, the Nernst linearization is a really smart linearization that allows us to simplify this equation in order to solve it in a more precise way. So basically we are imagining with the Nernst linearization simplification that this mass transfer speed could be described as a function of not an infinitesimal generic variations of concentration versus an infinitesimal generic variations in space, but as a function of two known parameters that are the concentrations of the bulk and the concentrations of the surface versus a well-known distance. So basically we are imagining with the Nernst linearizations to consider this as equal to an integrated variation of concentration versus a well-precise space. But what is this delta C and what is actually space? This this Nernst diffusion layer. This is the Nernst diffusion layer. So basically what we are doing is imagine to consider something like this. So we are transforming this exponential asymptotic trend in something different, more simple. So each single function could be associated with a specific line. A line that is between the concentration on the surface and the concentrations of the bulk. So in this situation, for instance, this delta C is the difference between this and this, so from 0 and C bulk, and in this case, delta C is basically the difference between this, C minimum, and C bulk. And the Nernst diffusion layer is basically this distance. So we are passing from a very generic equation to a more precise one, because this parameter is generic and this is generic, whereas this, since now we know what are the end and the starting points, is composed of two parameters that are known. This is known and this is known, and also this is known. And so with the Nernst linearization assumption, we are able to solve this equation. In which way? So let me cancel. Let's imagine to consider one generic concentration profile. So we have the migration of one species from the bulk to the surface. This is the bulk concentration. This is the surface concentration in these concentrations versus distance from electrode plot. So we know very well that in this case the mass transfer speed is equal to the diffusion coefficient for these variations in concentrations versus the distance, but we know that we can proceed with the Nernst linearization, and so we can rewrite this equation in this way. So this is equal to dE delta C over delta X, but delta X is basically this one, and delta C is C bulk minus C bulk minus C on the surface. And so we can say that the mass transfer rate is equal to this for this minus this over the Nernst diffusion layer. So Nernst linearization is the assumption, the Nernst diffusion layer is this integrated distance. And so this is a quite more simple equation, because it's equations containing known parameter. So we are passing from a differential one to an integrated one with the Nernst linearization assumption. And so now, remembering another aspect, remembering that the current could be connected as a function, the current density, for instance, of the rate, something that is close to what we have described speaking about the Butler-Volmer in general about the cinetic, we can say that the current is equal to the mass transfer rate for n for the Faraday constant. This is obviously true since this is an ampere over centimeter square. This is mole per second, and this is basically more per second over centimeter square. This is mole of electrons over mole, and this is coulomb over mole of electrons. So basically, if we want to look at the unit of measure, we can say that this is coulomb over second per centimeter square. This is basically a unit of measure of a flux, so is this one. This is mole of electrons over mole, and this is the Faraday constant, is coulombs over mole of electrons. So we can appreciate how basically the unit of measure is the same, and so this makes sense. Again, we are connected as what we have done for what concern the Butler-Volmer. Again, we are connecting some speed of a process to the current. In this case, the speed is not the speed of the reaction in terms of electron transfer, and so the rate that can be described in accordance with the Eyring equation or the Arrhenius one. But in this case, the speed is a speed that is a flux associated with the Fick's law described in this way due to the linear linearization that can be connected with the current again with this equation. So now we can eliminate here, and we can write that now the current is equal to n for the current density, obviously, if is the current only way to multiply for an area. In this case, is the current density for this, and so for these concentrations in bulk minus concentration in the surface on the Nernst diffusion layer. And this is the generic equations of a generic current associated with a certain generic mass transport effect, associated with a certain generic mass transfer. But what is happening if maybe we are now imagining to polarize more the electrode? Maybe our species that we are considering is a species that if we are polarizing negatively the electrode, you want to move in order to basically be transformed in a reduced one. So maybe we have here some oxidized species with a certain concentration, and on the surface of the electrode, this oxidized species is transformed in a reduced one. And this is the reason for which the concentration of the oxidized species on the surface is smaller with respect here, because here we have a conversion, and so the concentration is decreasing. But what is happening if we are polarizing more and more our electrode because we want to push strongly the systems in achieving this reaction? What is happening is that the speed in which these conversions occur is faster. And so what happens is that the concentration of these species on the surface start to become even smaller. So the one of the bulk is the same. But if we are polarizing more and more, and so if from a practical point of view we are moving more and more away from the equilibrium condition, the open circuit potential, what is happening is that we are increasing the overtension basically, because we are inducing a polarization that can promote a current, that can promote the reaction, so we are moving away from an open circuit condition. We are creating an electrolyze, we are with an electrolytic process creating overtension. And if we improve the overtension, since we are improving the polarization, the way in which these conversions occur is rapidly. And so even if the concentration is still remain the same, we are decreasing more and more in this way the concentration on the surface, and we are decreasing it until to reach the minimum value, and the minimum value is obviously 0. So we can proceed polarizing the electrode faster and faster until to reach the maximum concentration gradient. Why the maximum concentration gradient? Because the concentration in the bulk is again the same, but now the concentration on the surface is 0. And so, since this is 0, we have the maximum difference, because something minus 0 is equal to basically something. Because previously the concentration gradient, it was this one, and so this one. But now, since the process is going very speed, the polarization is huge, we have basically this difference, and so this concentration gradient is maximum. And what does it mean? That if we are polarizing even more the electrode, so okay, we are reaching this point, but maybe we want to polarize it even more, and so we are even increasing even more the overtension. What is happening? Nothing. Why? Because when we have reached this minimum situation, even if we are polarizing the electrode more, we are providing more overtension, we are not able to speed up the process anymore. Why? Because we have already reached the maximum gradient. And so the current associated with the maximum gradient that is connected with the difference between the concentration on the surface and the concentration of the bulk is the limiting current. So this current is the limiting one and is equal to N for F for E. This is the maximum concentration gradient, so C bulk minus 0, and so C bulk, and this is equal to this. So these parameters are basically constant, and so what does it mean? That the limiting current is proportional to what? To the bulk concentration. And this is the reason for which, by increasing the amount of species in the bulk, we are able to speed up the process. In which way? Not to speed up the process, but we are able theoretically to achieve a measured amount of maximum possible speed. And so the maximum current, the limiting current, is a function of the bulk concentration. Because here we are not able to push this smaller than 0, it does not make sense. But what we can do is add more of this species, increase the concentration in order to increase this. And in this way, yes, we can have an higher difference. So we can increase the limiting current, the theoretical maximum current that we can achieve, associated with the theoretical maximum speed of the process that we can achieve, only by increasing the bulk concentration. So now basically we can say that since now we have the difference between J and JL, we can make the ratio. And what's happened is that J over JL is equal to minus the concentrations of the surface is just a simple counting, a simple calculation over the chain bulk. And now, if we introduce this inside the function describing the overtension associated to the mass transfer, these overtensions are equal to T and F, concentrations of the surface over concentrations of the bulk. Why? Why we can say that the overtension of the mass transfer are described with these particular types of function? Well, it's quite simple, because basically I'm looking about the Nernst equation. I'm looking about a Nernst equation associated with a generic potential that is a function of the concentration on the surface, so the real one. But then we have also a Nernst equation that is associated with a potential that is the equilibrium one. So obviously all the Nernst equations are theoretically equations associated with open circuit potential. This is obvious, but here we are imagining to solve the Nernst equation considering in the basically has a concentration for the resolution of the Nernst equation, this concentration, whereas here we are considering the bulk concentrations. So it's basically a smart tricks in order to describe the overtension between an actual real process and equilibrium one. So basically we can say that the relationship between the overtension in the mass transfer is this one. But we know that exists a relationship between this and this. And so we can write this in another way. And we can say that RT over NF is equal to 1 minus J over GL, or module maybe. And so, what does it mean? That now, if we want to plot this function in a overtension current diagram, we can appreciate a trend like this, with the limiting current representing the asymptote of this function. And now, if we sum these contribute with respect the one of the Butler-Volmer, with respect the one of the ohmic resistance, we can finally obtain the well-known final trend that represents the actual real resolution of this function representing the descriptions of the salinity in any types of electrochemical process.